Okay, friends, one last video to kind of wrap up everything we've been chatting about today. Hopefully you're getting the feel for how statistics kind of works. Very often people, I think, use stat to prove things. I'm gonna disprove or support your theory with my statistics. I actually look at it completely differently. I look at it as, let's see what the numbers show us. For example, we flipped pennies in the example today. Now, in the back of your mind, you know that pennies are 50-50. So you knew that this percentage kind of made sense. It made a lot more sense than that silly 80% that you first saw. But statisticians don't go into the world knowing anything about percentages. For example, if you're an actuary and you're helping an insurance company figure out how much to charge their customers for policies, you have to figure out what the rate of certain things are. Earlier in the video, I took a fall in the hallway. I mean, people do that. You fall in the hallway, you fall in the shower, you fall on your driveway shoveling snow. At what rate does that happen? And of course the answer is, it depends on a lot of variables, and that's why actuaries are paid like 6 figures to figure that out. So statisticians, actuaries are a type of statistician, statisticians' job is to run experiments or look at available data and then come up with percentages based on that. That's what we did here. So a statistician would say, I flipped your coins 100 times, so we did 100 trials. Now what the statistician wants to know is, what is the average behavior of all the coins out there in the entire population based only on a sample of, say, 100 trials? So what they're actually after is what's called a parameter. We'll talk more about this next class. They're after the population measure. Well, we're not allowed to get that. We are allowed to get what are called statistics. This is an example of a statistic. More on that next class too. A statistic is a measure of a sample. And the reason this class is called probability and statistics and not probability and parameters is because if the class was called probability and parameters, it would be a very simple and very impossible class. So for example, if we were interested in knowing how pennies flipped and the class was called probability and parameters, I would say, okay, everybody, go out and get every penny on earth and flip them infinitely many times and keep track of what you've got. That's ridiculous. Nothing works like that in the world except for extraordinarily small populations of extraordinarily rare things. Statistics is a way of looking at an entire population through samples and then making conclusions based on it. So check this out. The statisticians, us, 49% of our sample were heads. But clever people amongst us will realize, well, wait a minute, Sean, if I flip 100 more coins, I might not get 49% heads. I might get more. I might get 52% heads. I might get 45% heads. I might get exactly 50% heads, and that is correct. That is called sampling variation. We're going to talk about that in this class too. Oh, we're talking about so much today already. So how do statisticians control for that? Well, they admit the fact that their sample of 100 is limited and has what's called sampling error in it. And they control that with what's called a margin of error. If you've had me in class before, you've heard this phrase before. A margin of error is a measurement that we put on a statistic to make its precision more reasonable. No one in their right mind would say, yes, I flipped a coin 100 times and I can report with statistical confidence that coins flip at 49%. No. What you say is the margin of error that accompanies this 49%, which FYI, in this case with 100 trials is 10%. Don't worry about how I got that. We'll talk more about that in this class. 10% is the margin on this. So no statistician worth their salt is going to say a 49% result of heads is exactly 49. They're going to say it's between 39% and 59%. See what I did there? I took that 10% and subtracted it from 49, and then I took that 10% and I added it to 49. That is what a statistician should come back at with from this experiment. Should. Now, thinking back to what started this entire thing, which was the NPR podcast, that 50-second thing we listened to earlier. That scientist did not give a margin. That scientist said, based on our research available from cloth masks, best we can figure is they're 50% effective. Well, where's the margin of error? There is no margin given. That doesn't mean there isn't one. There was one used in the study. Statisticians, unfortunately, have admitted that the general public doesn't like stuff like this. They want something neat and clean like 49%. They don't want this between. Well, I'm sorry to say, the reason you're in this class is because we have to understand this. This is very, very telling. As a matter of fact, if you look at this range of numbers, do you notice that 50% is between 39 and 59? That tells us something statistically. It tells us that if the statement is true, and if this was their data about masks, that they're no better than a coin flip. Because 50% is in there. We'll get more into that in this class, promise. We can also apply margins of error to smaller samples. Like, we could have stopped after 10 trials. Remember? 10 trials, 80%. Well, it turns out the margin of error with 10 trials is something like 25%, which effectively makes it useless. You're going to say something along the lines of, okay, I'm pretty sure that this coin is going to flip heads between 50% and 100% of the time, or something useless like that. So the moral of the story, really, is that all things being equal, more data is better than less data. And even if you've done a really, really good sample with really, really good randomly selected items in your sample, you're still going to have this idea of error that you have to adjust your sample statistic with. Okay, we've got a lot of ideas today. I just love the fact that all of this came from a bike ride home yesterday. I can't wait to see what today's bike ride brings.